All right, hello, this is Mr. Allison. Quarter 3 of the 2020-2021 school year. This is assignment for Honors Physics 10.2, a Phet lab on gas laws. And we're just going to explore the way gases behave a little bit. So I'll click there, and this is we're supposed to go to the Phet simulation, gases, and intro. So here we go. That's from the previous video. All right, so we're going to Phet lab. So we just went into Phet, you know where that is, and then simulations, physics, and then what are we getting at? We're getting at gases intro. I'll go down here, F there in alphabetical order. There's gases intro right there. All right, I'm gonna start that thing up. I'll hide that, and we'll just stay with intro right there for now. Let's see what we're supposed to do. And I'm not gonna write down the whole stuff for the lab. I'm just gonna kind of walk you through it, because you do still have to do the lab, but I'll kind of get you through it. So hopefully we'll be able to walk through this in about 15 minutes or so. Click the green plus sign to open the particle box. Pump 100 heavy blue gas. You know what? I think we're going to have to do 2 screens for this one, because that's a lot of instructions. So hopefully this is supposed to, my screen recorder is supposed to, there we go. Let's make that smaller. 50% maybe. There we go. That's enough. I can see that. I don't know if you can see that or not, but I could see that just fine. And then let's go like this. Break that one off. And hopefully that'll work at a smaller size also. Sorry for doing this on the fly, but that's what happens when I have to start doing a lot of makeup stuff, right? Okay, so there's that. And there's that. Okay, well, that's working pretty good. Okay, so let's do that. Got that. Let's make that a little bit happy. Oh, okay. All right, I just want to make this a little bit bigger. There we go. All right, so that should be good. All right, so it says click on the intro, and you might want to do this on your own computer too, because these instructions are pretty detailed. Okay, let's see. Pump 100 heavy blue gas molecules into the chamber. So we select blue ones, and then this button here, add particles. And I don't remember what these buttons do. That's 50. Okay, so the double arrow is 50. Probably the single arrow is 1 or 10. So there's 100. So we just pumped 100 blue molecules into the chamber. Explain their behavior. Do they move fast or slow? Do they move curved or straight paths? What happens when they touch other gas molecules? Okay, so are they moving fast? That's part of the question. So I'm going to click the stopwatch. That stopwatch is in picoseconds, which are very small. So they look like they're moving slow, but they're actually moving extraordinarily fast right now. And because gas molecules do move extraordinarily fast. Do they move in curved or straight lines? No, they're always straight. Why? Because Newton's first law, a body in motion stays in motion unless it's acted upon. And so they're going to run in a straight line until they crash into something else or the wall, and then they're going to go into another direction. It's just like pool balls, unless you put English on the pool ball, of course. If you're playing regular pool, the balls go in a straight line, right? What happens when they touch each other? They bounce off, and that's an elastic collision. The energy can be transferred. If you watch them closely, like a fast one will hit a slow one, and then the fast one will be going slow, and the slow one will be going fast. But that is a nearly elastic collision there. Okay, it says now click the red dot under the pump that represents a smaller gas bottle. Pump 100 smaller gas molecules into the chamber and explain how their behavior is similar or different. Okay, there's 100. The smaller gas molecules are moving faster, aren't they? That's not so surprising. And when they bounce off the larger, heavier molecules, they don't affect the larger, heavier molecules near as much, right? Just like when a big person runs into a little person, it's a little person who goes flying, right? And if you've ever played football, you know all about trying to tackle a big person versus a little person. So the smaller molecules are going faster, but notice they are all, both types of molecules are all spread out. And if you watch carefully, you might see a little cohesion for a moment, but the energy, though, always knocks them apart. What's the relationship between the size and the speed of the particles? The smaller particles are faster. That's not, I don't want that. Close that. Okay. And it's a Phet lab exploration. So let's open it up. It's just not what I want. And so, sorry about that. I'm gonna minimize that so that doesn't happen again. There we go. Okay. Where were we? What is the relationship between the size of the particles and speed? What type of okay, so the smaller particles are faster. What type of relationship is this? Directly proportional or inversely proportional? Well, as the size gets bigger, the speed gets smaller. So that's going to be inversely proportional because as one measurement goes up, the other goes down, right? As the particle gets bigger, the speed gets smaller. So that's inversely proportional, and you could, sketch that there if you want to. Okay, temperature versus pressure of particles. Click the heat control. Yeah, this is going to be a long lab. Click the heat control handle on the bucket below the gas chamber. Drag it up to increase the heat to 500 degrees Kelvin. So right now it's 300 degrees Kelvin. You can see at the thermometer right there. Above the box, there's a thermometer with the red thing. And then also there is the readout. So now we're watching what happens when we increase it to 500. We're adding energy and increasing it to about 500. It doesn't have to be exactly 500. So what happened? Where's the pressure? Okay, so there's 40 atmospheres. That's a measure of pressure. I'm going to take it back down to 300. Notice the pressure's going down. And when I add heat, the pressure goes up, right? Because the pressure, I don't know if it's going to say this, but the pressure of something is just it's a measure of how many molecules are striking the edge of the container, specifically wherever the gauge is, but on average, they're striking the walls of the container all the way around with the same amount of force. So wherever you put the pressure gauge, it's going to be the same, give or take, unless there's a tank so big that gravity comes into play. But so the pressure goes up when the temperature goes up, because when the temperature goes up, you've added energy to the molecules and they're moving faster, which means they're striking the edge of the container harder, and that is pressure. All right, now increase the heat to 1,000 degrees Kelvin, and what is the pressure now? So 41, now we're going to go up to 1,000 degrees Kelvin. And it's 82, so it's roughly twice, right? Roughly double. What is the relationship between pressure and temperature? So the relationship is, as you increase the temperature, the pressure goes up, and it's directly proportional. Because as one goes up, the other goes up. If you take the temperature down, then the pressure is going to go down. So you need to draw a graph of a directly proportional thing. Is that even still recording? Yeah, there it is. Okay. Oh, we better be recording the whole thing and not just. Oh boy, I want to record the screen. I wonder if it's just recording the window. Okay. Gosh. I don't even know how to check. Okay, well, I'm just going to go through it, and hopefully it's recording the whole window. It may not be, though. All right. Okay. So a graph of something that's directly proportional is going to look like this. As the temperature goes up, the pressure goes up. Just for your knowledge, an inversely proportional graph looks like this, right? As this goes up, as that gets more positive, this gets more negative. So that's the way that works. All right. So let's see, what's next here? Now we're talking about volume versus pressure. Reset the system by clicking the orange button. There we go. I don't know if you can see that. Click the orange button on the lower right. Click on the collision counter to open the wall collision window. Set the sample period to 20 picoseconds. So what am I doing? There's particles. Do I need to go to the other sim maybe? Because I don't see the kind of controls they're talking about. Click on the collision counter. Do you see? Oh, there's the collision counter. Okay. Oh, I see. There we go. Okay. So click on the collision counter, wall collision. Set the sample period to 20 picoseconds. Okay. Click the green plus sign to open the particle box. Pump 100 heavy blue gas molecules into the chamber and then 100 light red molecules and allow them to spread out for 20 to 30 seconds. Okay. There's 100 of those and 100. Oops. There's 100 of those. Okay. So we got to let them all wait till they get all spread out. And remember, gas doesn't spread out. This is dramatically slowed down. This timer we're going to use is a picosecond, which is a trillionth of a second. So that's kind of just, I'll put the stopwatch up here too. And so that's in terms of the sim, that was 11 trillionths of a second in how fast things actually happen. Okay, so that's spread out enough. Let's see, click the go arrow to measure the number of collisions in 20 picoseconds. Go. So that's 609. Next one. And he wants us to do this a few times. And what we're going to find out is that it's going to be similar, but not the same. Because when we talk about pressure, we're talking about the average number of collisions, wall collisions in a particular time, not the exact count. 565. We'll do it one more time. 573. Let me do it one more time while I'm reading the next instructions. Now select the width checkbox at the right. Note a dashed line with arrows will appear below the chamber, indicating the width is 10 nanometers. That's 1 times 10 to the 9th meters. So it says I can get the width. There, okay. All right, so there's 10 nanometers. All right. 1 nanometer. Record the maximum chamber width, speed of the particles, and current temperature below. Okay, so you got to write down how wide the chamber is. Is that the maximum chamber width? Okay, so it says record the maximum chamber width. So I guess that's what we're doing there. We've dragged it open. And you're going to record the chamber width, which is 15 nanometers. What's the temperature right now? It's 365 degrees Kelvin. The pressure, where's the pressure? It's 18.9. You can use atmospheres or kilopascals, either one, whichever you want to do. And then the average wall collisions. So let's go like that. And we're going to see it's lower because the thing's bigger. 492. Oh, okay. We were supposed to leave it at 10, and then we were supposed to drag it to 15. So that doesn't matter. We're learning about it either way, okay? So So the first one, if you're following along with me, that is at with a width of 15 nanometers, and then we're going to slide it in to 10 nanometers, which was the original one, and we'll see what happens to everything there. Notice that the pressure just popped up. So now let's check the average wall collisions, and see how many there are there. And what would you expect if you have a same amount of particles in a smaller area? You're going to get more wall collisions, aren't you? And if you get more wall collisions, that's going to be more pressure. And the wall collisions, there's the same amount of energy of all these things flying around in a smaller space, so the temperature is going to be higher too. And you can think of that in terms of the energy, the same amount of energy in a smaller space. If you want to think about it that way, you can think about it as the collisions creating the heat. So when you take the same amount of molecules in a smaller space, you're going to have more collisions, which is going to create more heat, create a higher average kinetic energy, because you've got the same kinetic energy on the molecules, but you put them in half a space, so the average kinetic energy goes up. So that's the temperature. And then it says, click on the gas chamber's left-hand channel and drag the wall as far as to the right as it'll go. So now we're going to close it way up, and it goes down to 5 nanometers. And notice the temperature, the pressure went up. Okay, so there's 10. The pressure is 2,911 kilopascals. We cut the volume in half. We dragged it down to 5 nanometers. Now the pressure is 5,752 kilopascals. Now it's keeping the temperature the same, but that's not. It's doing that. It's like it's set to hold the temperature the same, so you can do other variables. When there's more than 2 variables, it becomes more difficult to figure these things out. So let's do the average wall collisions now. And see, you can see they went way up. Why? Because everything's still flying around, but it's hitting the wall more often. So the pressure went up. Average wall collisions, right? What's the relationship between the number of wall collisions and pressure? Well, the higher the number of wall collisions, the higher the pressure, because that's what it is. So that is a directly proportional relationship, so draw that. What is the relationship between the volume of the chamber and the pressure? Well, the bigger the chamber, the lower the volume, right? Because you've lowered the average number of wall collisions, because the wall's giant, and also the molecules have much further to travel before they strike the wall. So I just made it big again. I hope you can see it. I don't know if you can. But I did put, so now the average number of wall collisions in 20 picoseconds is quite a bit lower, right? Because it's all spread out, the molecules have farther to go, there's a lot more wall space for the same amount of molecules. So that's inversely proportional, right? The larger the space, the lower the average number of collisions. Okay. Click the laws icon at the bottom to switch. I do not see the laws icon at the bottom menu to switch tabs. Let me back up one. Maybe you can't see it from here. Okay. Laws. There we go. All right, so now we're on laws. Click the green, open the particle box, pump in a heavy 100 of the molecules of each, and allow them to spread out. And we'll read while we let them spread out. In the hold constant menu, select the pressure. Okay, so now we're going to hold the pressure constant. And we're just kind of exploring these things. Now select the width. Let's see, select pressure. Now select width checkbox at the top right. Okay. A dashed line with arrows appears indicating the width. We know what that does. Record the chamber width, temperature, and pressure. So we've got a temperature of 300 Kelvin. I'm going to change it to kilopascals. A pressure of 2366 kilopascals, and a chamber width of 10 nanometers. Now we're going to take the heat control and increase the temperature to 400 degrees Kelvin. Oops, I went a little past. All right, now what happened? Read the current chamber width. Okay, so we were holding the pressure constant, so the chamber width had to expand to accommodate the increased energy, right? Chamber width, pressure, and temperature now. We increased the temperature, which increased the kinetic energy of the molecules, and which would have increased the pressure, except we told the system to hold the pressure constant, so it had to change the size of the container instead. What happens when you try to increase the temperature to 500 degrees? Up, it won't go, because it's just outside the parameters of the system, right? That doesn't mean it can't ever be done. It just means this thing's not programmed to do that. So the relationship between the temperature and the volume, if you hold the pressure constant, if you want the same pressure and you add energy, right? If you want the same pressure and you add energy, then you have to expand the box. You have to expand the volume. So what kind of relationship is that? If the temperature goes up, the size goes up. So that's proportional, right? Because they both go positive at the same time. All right, we're nearly the end here. Now reset the system by clicking the orange circle. Boom. Far right. Click the green. Okay, we're going to add, let's see, we're going to add 100 of each again. That's its favorite thing. Okay. And let them spread out. In the hold constant menu, now we're going to hold the pressure constant instead. Okay. So the system is artificially rigged, so we cannot change the pressure at all. We're going to change other parameters and see what happens, right? So we're going to record everything, the number of particles, chamber width, temperature, etc. And now what are we going to do? Increase the number of particles to 1,000. So there are 500 heavy blue particles and 500 light red ones. And it's going to keep the temperature, the pressure the same. What do you think is going to happen to the temperature, for instance? So we'll go up to 500. Oh, I did something. I got to reset it. Okay, so okay, so we put those in there. And what are we trying to hold? We are trying to hold the pressure constant now, right? Or is that what? Oh, see, when you hold the pressure constant, it can either vary the volume or vary the temperature. That's interesting. Okay. So we're going to hold the pressure and volume constant. That one right there. And now we're going to add more molecules. And what's going to happen if we add more molecules? It's going to increase the number of collisions, which is going to do what? If we don't, we hold the pressure and let the volume change. Oh, I see. That's holding the pressure and letting the volume change. Okay. Oh, we were supposed to hold the volume constant. Okay. So let's go back down to 100 of each. And we'll take that volume back down to 10. Let me see the width so I get it right. $10, okay. So we're going to click this one, and that says pressure and allow the temperature to change. So we're going to hold the volume constant also. Now what's going to happen if we allow the temperature to change when we add? Well, if we add all those molecules and we want to hold the pressure constant, what has to happen to the temperature? It has to go way down, doesn't it? Because the temperature is the average energy, right, of all the molecules. And if you have all that many molecules, the temperature has to go way down because it's the average energy. I'm not sure if I said that very clearly. If you're trying to hold the pressure constant, so if we allowed the pressure to rise, then those things could be moving faster, right? But since we're saying we're going to add all these molecules, which means we're going to add all these collisions, but we don't want the temperature to change. We don't want the pressure to change. We want to add all the molecules, so we add all the collisions, but we don't want the pressure to change. Well, the only way you can do that then is to decrease the kinetic energy of all these collisions, because you've just added 3 times as many collisions, so they have to happen 3 times as slow. Don't do the math on that, but they have to have the collisions kinetic energy has to be a lot slower in order to not increase the pressure. And how do you decrease the kinetic energy of the molecules? The temperature is the average kinetic energy of all the molecules, right? So there you go. All right, we're almost. This was a long lab. I remember this. Okay, reset the system. The system is reset. Let's see. 100 particles each. Let them spread out while we're reading. In the hold, I see. In the hold constant volume, select pressure with T. So pressure and allow the temperature. Is that? This is not the most well-written lab, is it? So just make sure you're kind of messing with it and getting an idea. Let's see, select pressure with temperature variation. Okay, so we did that. We got the pressure with the temperature variation. So now you're going to record all your numbers. And then what are we going to do? We're going to add 50 more blue particles and 50 more red particles. And then we're going to drag the chamber wall to the left until the temperature matches the initial temperature. So we're going to add 50 more, and we're going to open it up till it goes back down to 300 Kelvin. There we go. Record the total number of particles, the chamber width, and the pressure and the temperature. What is the relationship between the number of particles and the volume of the chamber when the temperature and pressure are held constant? Well, if you add more particles and you don't want the pressure or the temperature to change, then you have to open up the box more, right? Because that has more wall width. So the average, the odds of a collision happening are lower because you got the same number of atoms in there, but much more wall space, right? Plus, also, the atoms have to fly further to get from one wall to the other, so the rate of collisions also goes down. So the relationship between the number of particles, the volume of the chamber, that's a really weird question. What is the relationship between the number of particles and the volume of the chamber if you are holding the temperature and pressure constant? Well, as the number of particles goes up, the volume of the container has to go up, right? If you want to hold the temperature and pressure constant. So that's directly proportional. Okay. The last little thing is the ideal gas law, and you can just look that up. Google that and write it in there. It's a temperature. It has to do with pressure and temperature and volume. And so it's a little complicated when you have all these different interrelating variables. So anyway, that's it. And I don't know for sure if this recorded the whole screen or not, and I'm about to find out. Bye.